All right. We're going to talk about the gas phase. So, gases, as we have discussed previously, one of the phases of matter and one of their important properties is that they have an indefinite shape and an indefinite volume. So, solids, defined shape, defined volume. You have a cube of something, it's that cube of something. Liquids, defined volume, but indefinite shape. So it takes the shape of the container, but it all sits at the bottom, right? Um, Gas, on the other hand, takes the volume and shape of whatever container it's in, so it kind of floats around freely. And when we're talking about gases, there are four major variables we want to consider. The first is pressure. Pressure is simply force over an area. You don't really need to worry about that too much, but one of the major variables we're talking about is pressure. And there are a lot of different measurements and units for pressure, but the one that you're most likely to encounter is millimeters of mercury. So, Italian guy, Evangelista Torricelli, way back in the day, I think 1600s, made a device where he basically got a glass tube with mercury in it. And then as he walked up a mountain, he noticed that the pressure was dropping, and he saw that the amount of mercury in his tube was dropping as well. And so when the measurement of millimeters of mercury is literally how many millimeters of mercury are in the tube. So this is also called, so you'll see the abbreviation mmHg, but it's also called torr, T-O-R-R, after Torricelli. This is the most common one you're likely to encounter in Gen Chem. So 1 millimeter of mercury is equal to 1 torr. These are interchangeable units. They're the same unit. And 760 millimeters of mercury is 1 atmosphere. These are the two most common pressure units you're going to encounter in chemistry: millimeters of mercury, or torr, same thing, and atmospheres. There are a lot of other pressure units: pascals, bars, pounds per square inch. If you need a conversion for those, you'll have to go look them up, because there are a lot of different ones, but they're used in different contexts. So for the chemistry context, the most likely the ones you're going to see are millimeters of mercury, or torr, again, same thing, and atmospheres. The other unit variables we want to look at are temperature. Temperature has to be in Kelvin, because you cannot have negative numbers. As you'll see when we do our gas equations, you cannot have negative numbers, because then you might end up with something that gets a negative volume, which doesn't make sense. So you have to, it has to always be in Kelvin. Whenever you're doing gas stuff with gases, you must have your temperature in Kelvin. Volume is our other major variable. Generally speaking, liters, but milliliters will also be used quite a bit. Moles are moles. So that one's not the big of a deal. Well, those are the four variables that we're gonna look at: pressure, temperature, volume, and moles. And these get combined into gas laws. So there are three major gas laws, and then a combination of them. So the first gas law is Boyle's law. So this is, I believe, John Boyle. I'll get all these names and countries mixed up, but John Boyle, I believe, English chemist, maybe British chemist. He might have been English, but I think he was English. So Boyle's law basically says that at a given temperature, so the temperature is constant, pressure times volume is constant. So the pressure and the volume multiplied together are constant at a given temperature, which means that pressure is inversely proportional to volume. Okay? Pressure is inversely proportional to volume, meaning that as you increase the pressure, you decrease the volume. As you decrease the pressure, you increase the volume, and vice versa. So you can, generally speaking, you'll be changing the volume, right? So if I have the volume, I'll double the pressure. If I double the volume, I'll have the pressure, right? So as volume increases, pressure decreases. As volume decreases, pressure increases, okay? And so if you remember when we talked about dilution, the dilution equation is M1V1 equals M2V2. Well, the gas law has a very, very similar equation, and that's P1V1 equals P2V2. P1V1 equals P2V2. So let's look at an example. You have a syringe that has 10 milliliters of gas at 500 millimeters of mercury. What will the pressure be if the plunger is pressed so the new volume is 5 milliliters? Okay. So whenever you get a gas law problem, the first thing you want to do is you want to identify what variables, well, first of all, what law are you applying, and then what variables do you have? So we know we're doing Boyle's law. So we say, okay, P1V1 equals P2V2. Let's identify. 10 milliliters, that's our initial volume. So that's V1. 5 milliliters, that's our second volume. So that's V2. And then 500 millimeters of mercury, we see that's our initial pressure. So that's P1. We're solving for P2. So we want to know what's the pressure afterwards. So we're going to rearrange our equation to isolate P2. So P2 is equal to P1 V1 over V2. So we just plug the numbers in. 10 milliliters times 500 millimeters of mercury divided by 5 milliliters. Milliliters cancel, and you'll get your answer in millimeters of mercury. So you find that, hey, look, I halved the volume, and so I doubled the pressure. Now, the units that you use do not matter as long as you have the same units on both sides. Charles' law, next law. Charles' law, this is a French guy, I'm pretty sure, Jacques Charles, I believe. When pressure is constant, the ratio of the volume to the temperature is constant, or volume divided by temperature is constant. And this is saying that volume is directly proportional to temperature. So, as temperature increases, volume increases. As temperature decreases, volume decreases. And so on and so forth. You can see this if you have a balloon. If you've ever seen a balloon dipped in liquid nitrogen, you notice that suddenly it's a lot smaller. So volume and temperature are directly proportional. As one goes up, the other one goes up. And generally speaking, you're controlling the temperature. But as one goes up, the other goes up. And we write this. So similar to Boyle's law, we can write out an equation to find what happens if we change the volume or the temperature. And that's V1 over T1 is equal to V2 over T2. So an example of a Charles' law problem. If a syringe containing 40 milliliters of gas at 10 degrees Celsius is submerged in a water bath until the temperature is 90 degrees Celsius, what is the final volume of the syringe? So once again, we know it's a Charles' law problem, so we know we're using this equation. And so we need to identify what variables we have. Okay, well, 40 milliliters, that's our initial volume. And 10 degrees Celsius, that's our initial temperature. So I've found V1, I found T1. And then the other thing I have is T2, and I'm looking for V2. So to rearrange this, V2 is equal to V1 times T2 divided by T1. So I'll plug these in. Now remember, it has to be in Kelvin. It has to be in Kelvin. Because imagine if I had a negative, because you can have negative Celsius, right? If it was negative 10 Celsius, then you'd end up with a negative volume. And that doesn't make any physical sense. So you always have to have Kelvin when you're doing gas law problems. So you just plug these numbers in. Again, Kelvin will cancel. You'll get milliliters. And you find that the answer is 51.3 milliliters. Now we can combine Boyle's and Charles' law into the general gas law. So P1 V1 over T1 is equal to P2 V2 over T2. So it's literally just, I slapped Boyle's and Charles' law together, and it's called the general gas law. So a balloon at sea level, 1 atmosphere, at 25 degrees Celsius rises in the atmosphere until the pressure is 0.31 atmospheres and the temperature is negative 45 Celsius. At this point, the volume is 22.41 liters. What was the initial volume of the balloon? So again, we gotta put out our equation and isolate our variables. P1, 1 atmosphere, 25 degrees Celsius, that's T1. 0.31 atmospheres, that's P2. Volume in liters, that's V2, right? So that's V2. So we're looking for, and negative 45 is our T2. So we're looking for the initial volume. So we got to rearrange our equation, which I know this kind of looks like a mess, but we got to rearrange our equation so that V1 is equal to P2 V2 T1 over P1 T2. So again, it looks messy, but I just multiplied him up here and divided him down there. So you plug all that in, 0.31 atmospheres times 22.41 liters times 298K divided by 1 atmosphere times 232K. Again, if I kept it in Celsius, I'd end up with a negative volume, which makes no sense. Cancel atmospheres, Kelvin cancels, and I get liters. And I get my initial volume was 8.9 liters. Avogadro's law. We talked about Avogadro with Avogadro's number. And as you might expect, his thing has to do with moles. Volume is proportional to moles if temperature pressure constant. So if you had a balloon with n moles in it and you double the moles, you would double the volume. This one's pretty straightforward. You got double the volume, moles, double the volume. So let's do some practice with these laws. If a 2-liter canister under 900 millimeters of mercury of pressure is subjected to 3,000 millimeters of mercury of pressure, what is the new volume? So this is Boyle's law, right? So P1V1 equals P2V2. This is 2-liter canister, so this is my V1 is under 900, so this is my P1, this is my P2, and I'm looking for V2, okay? So V2 is going to be equal to P1, V1 over P2. So it's 2 liters times 900 torr, or millimeters of mercury, divided by 3,000 torr. Hey, torr cancels, and you're going to get 0.6 liters. Question 2. If a balloon with a volume of 1.5 liters inflates to 25 liters, when the temperature increases to 145 Celsius, what was the initial temperature in Celsius? Okay, so here I'm doing V1 over T1 equals V2 over T2. Okay, here's my V1, here's my V2, and here's my T2. So I'm looking for T1, which is equal to V1 T2 over V2, which is equal to, again, remember I need to convert this to Kelvin, so add 273. So it's 1.5 liters times 418 Kelvin divided by 25 liters. You find that it's you get 1.5 times 14 divided by 25, and you get 25.08 Kelvin. And if you convert that to Celsius, so you subtract 273, you get negative 247.92 Kelvin, which is pretty darn cold. Ignore that. All right. Then finally, a syringe with a volume of 500 milliliters is at 300 Kelvin. The syringe is cooled to 100 Kelvin and the volume is reduced to 30 milliliters. After this, the pressure in the syringe is found to be 0.45 atmospheres. What was the initial pressure? All right. So general gas law, P1 V1 over T1 equals P2 V2 over T2. And we've got V1, T1, T2, V2, and P2. So we're looking for P1. Okay, so I'm going to multiply that there. So P1 is equal to P2 V2 T1 divided by T2 V1. So P2 is 0.45 atmospheres. V2 is 30 mils, and T1 is 300 Kelvin. Kelvin. And then dividing by 100 Kelvin times V1, which is 50 mils, and you punch all that in, and you get, 0.81 atmospheres. So it really is it's just a function of identifying here are the variables, or here's the law I need to apply. here are the variables, and then just plugging them in, making sure that the units need to be the same on both sides, and that the temperature has to be in Kelvin 100% of the time.